Hello and welcome to this lesson on Data Sufficiency Word Problems on the GMAT quantitative section. So let's start by just talking about the question frequency and format for these word problem data sufficiencies. There'll be approximately half of the 15 to 16 data sufficiency questions in a given quantitative section, so about 8 problems, and they're going to have the same 5 constant options correlating to which conditions is or are sufficient to provide a definitive answer to whatever the question posed is. And those answer choices, of course, are still going to be A means that statement 1 but not statement 2 alone is sufficient. B means that statement 2 but not statement 1 alone is sufficient. C will mean that the statements together but neither alone is sufficient. Choice D will mean that each statement alone is sufficient, and choice E will be that neither statement alone nor together is sufficient. Then you'll have the same 2 types of data sufficiencies for the word problem data sufficiencies, value or yes, no. Now, the strategic implications are that you really, with these longer word problem data sufficiencies, want to minimize the impact of long given statements and conditions by translating the English into math. And you'll do that by deliberately evaluating what is known and needed as algebraically as possible from the given statements to start. And then you'll want to use initials and shorthand to efficiently define variables for each unknown. So if you're talking about Frank's sheep versus George's sheep, you can say, well, Frank's sheep will indicate that with an F, George's sheep will indicate with a G. And you'll also want to recognize that frequently one evaluation, either an individual statement or the initial conditions, can be significantly longer than others with these word problem data sufficiencies. So recognize that you may have a lot of work to do for statement 1, but then statement 2 goes really quickly, and even combined it goes really quickly because you did the majority of your work in statement 1 or statement 2, whatever it may be. So then, when it comes to data sufficiency word problems, what you're really looking at are systems of linear equations. And you have to remember the golden rule, as it were, for linear equations, which is that to solve for a single variable requires a single equation. So if we've got a variable of x, we need one equation to solve for that variable of x. Now, for linear equations, as it pertains to these data sufficiency word problems, we know that solving for 2 unique variables will in theory require 2 unique equations. So if I've got variable x, variable y, I'm going to need 2 equations in order to solve for x and y individually. And theoretically, solving for as many as, say, 74 arbitrary number unique variables will theoretically require 74 unique equations. And the way this all relates to data sufficiencies is that it produces our default data sufficiency word problem need, which is x unique variables for x unique equations. So if I'm trying to solve for 3 different variables, I'll likely need 3 different equations. Now, you don't unnecessarily have to solve for the exact value. If you determine you have an equal number of equations to the equal number of variables that you have, you know you can solve, and you don't actually have to spend the time doing it because of the format of a data sufficiency. You'll also want to note algebraic paths to specifically sought variables. So if you're being asked for the combination of x, y, that doesn't necessarily mean we need to solve for x and y individually. Similarly, we need to recognize that inequalities do not function identically to equations. So what that means is you can't say, well, if I get 2 inequalities, I can solve for 2 variables. Inequalities don't have one specific solution, so they don't function the same way. However, inequalities with all values greater than 0 can be manipulated in the same ways as equations can. So what that means is you can add, subtract, multiply, or divide, provided that everything in the inequality is greater than 0. Because there is the catch of if you multiply or divide by a negative, you have to remember to flip the sign in your inequality, and that can cause some complications when working through data sufficiencies. So let's consider a sample word problem value data sufficiency. So we've got this situation with Brant, Carl, and Earl. They're each paid a different constant rate for each bag one of them produces at Duffel Industries. And we're asked how much does Carl get paid for each bag he makes at Duffel Industries, the specific value. Now, always articulate what you know first, and we're going to just shorthand Brant's rate as B, Carl's rate as C, and Earl's rate as E. Simple enough. And then, of course, we'll box off Carl's rate as the value that the problem is seeking the answer to. Then we have our default need, which is x unique equations to solve for x unique variables. In this case, we have 3 unique variables, b, c, and e, referring to the 3 respective rates. So we need 3 new equations with no new variables. So then we have to consider the statements, starting with statement 1. So statement 1, Earl's rate per bag is twice that of Carl. We can articulate that as E is equal to 2C. And 1/3 of Brant, meaning Earl's rate, is 1/3 of Brant's. So that means E is equal to 1/3 B. We have 2 equations, not 3 equations, so therefore it's not sufficient. And we don't have to manipulate the algebra any further. We know that the options remaining are going to be B, C, or E. Then condition 2, we see that Brant makes $200 more per bag than Earl does, so B is equal to 200 plus E. Considering this equation alone, we just have 1 equation, we don't have 3 equations, so we can eliminate choice B and condition 2 alone. Then we'll combine the two statements, and we realize that together we have 3 unique equations for 3 unique variables, and theoretically it's sufficient and we don't have to fully solve. The equations are clearly different, which allows us to simplify this and just go, okay, we know that's the right answer. And so select choice C, the conditions together but not alone are sufficient, and we have our correct answer without fully solving for exactly what Carl's rate was. Now, let's take a look at a similar but slightly different yes-no data sufficiency. So, similar situation, got a story about Duffel Industries received an order for 10 bags consisting of 2 of its bag models, the Amani and the Goody. If each Amani bag costs $25 and each Goody costs $75, are there more Amani bags than Goody bags in the order? So once again, we'll start with what we know, and there's a lot in this introductory paragraph. So first, we're going to assign variables for the number of bags, and we know that A can be the variable for the number of Amani bags, G can be the variable for the number of Goody bags. We then know that A plus G, the number of Amanis plus the number of Goodies, is equal to 10 from the opening sentence. We also know that G is equal to 10 minus A, and since we're being asked a question about the Amanis in relation to the Goodies, we probably want to do that manipulation up front because it's probably going to be helpful. Then we also know that the cost of an A is $25 and the cost of a G is $75, and then we get to the question, is A greater than G, yes or no? Always write out the yes/no to make sure you don't lose sight of that, because we don't need the exact value of A or G. We just need to consider our no, which is one inequality definitively relating A to G. So then we get to the statement, starting with statement 1. So total revenue from the bag order was less than $550. So 25A plus 75G is less than $550. At this point, we can substitute 10 minus A for G, and we get 25A plus 75 times 10 minus A is less than 550. Now we just have some manipulation to do. So we'd add 50A to each side, because of course 25 minus 75A is going to be minus 50A, and subtract 550 from each side to simplify our inequality as 200 is less than 50A. Divide by 50, we find that 4 is less than A, and because A is only greater than 4, well, A could equal 5, in which case, no, there are not more Amani bags than Goodies in the order, but A could also equal 6, which would be a yes, there are more Amani bags than Goody bags in the order. So since we've got both an outcome of yes and an outcome of no, this condition is not sufficient, and our options will once again be B, C, or E. So then we go to condition 2, again articulating it as algebraically as possible. So 450 is the total revenue for the bag, or sorry, the total order revenue for the order was greater than 450 this time. So 450 is less than 25A plus 75G. Same general approach, substitute 10 minus A for G. So you get 450 is less than 25A plus 75 times 10 minus A, the quantity. And then we've got to do a little bit of combination and manipulation again. So 450 is then less than 25A plus 750 minus 75A. Do a very similar manipulation, add 50A and subtract 450 on each side to determine that 50A is going to be less than 300. If you divide 50 by 6, now A is less than 6, meaning that our maximum A value is 5, and our answer is always no. And you have to remember that both always yes and always no are sufficient when it comes to the statements on a yes-no data sufficiency. So because we've determined that the answer is always no, there are not more Amani bags than goodie bags in this order, we would select choice B, and that would be our answer. So, as always with data sufficiencies, our process is going to be very consistent. So you want to algebraically articulate the given conditions by assigning variables to all provided unknown values while asking those same three questions as always. First, what do I know? Note it with a K. What am I looking for? Note the question with a box. And if it's a yes-no format, put the little yes-no or Y/N. And then lastly, what do I need to find what I'm looking for? And you'll note that with an N. Again, all of this as algebraically as possible without really diving into the English from the paragraphs. Then step 2 is going to be to carefully articulate and manipulate statement 1 algebraically. And you saw we had to do some manipulation, and that's going to become something you'll want to be very clinical with. And of course, if statement 1 is sufficient, choices A and D will remain viable. If statement 1 alone is not sufficient, then your options are going to be B, C, or E. Then we get to step 3. We'll want to carefully articulate and manipulate statement 2 alone algebraically. If 1 and 2 are each sufficient, you'll select D. If 1 is sufficient but 2 is not, you'll select A. If 2 is sufficient but 1 is not, you'll select B. And if either choice is sufficient, you stop here. Remember, don't continue to working them together if one of them alone is sufficient, because then you'll trick yourself into a C, and we don't want to do that. But if neither 1 nor 2 alone is sufficient, your choices C or E are all that will remain viable. And then step 4, if necessary, is going to be to carefully articulate and manipulate the statements together algebraically. And a lot of the work that you did earlier will probably lead into evaluating the algebra together as well. And you saw that it became a lot easier in that last example with the yes-no regarding the goodie and the Amani bags. We already did the manipulation for the inequality in statement 1, and that made it more easily replicated in statement 2. And then, of course, if together the statements are sufficient, you'll select choice C, but if they are not, you will select choice E. So now let's go ahead over to the whiteboard and take a look at a couple more examples of word problems that you might experience on the GMAT quantitative section. Okay, so we have a sample data sufficiency word problem here. And we'll, of course, begin by just articulating what we know as we read through the opening statements. So, if Eloise bought only 25-cent and 20-cent stamps at the post office, well, let's first just define the number of 25-cent and 20-cent stamps as A is equal to the number of 25-cent stamps. And we'll say that B is equal to the number of 20-cent stamps. We also know that she bought at least one of each denomination, so that means that A is greater than 0, B is greater than 0. And then we're being asked ultimately, what is the number of 25-cent stamps that she bought? And we just box that off to make sure we don't lose sight of what we're being asked to solve for. So then we've got to consider what we need. And in this case, we've got two variables, A and B, representing the number of 25-cent and 20-cent stamps. And we know that our default data sufficiency word problem need is going to be x equations for x variables. So this time it's going to be two new equations with no new variables. Because, of course, if we added a variable, we'd need a new equation, and we want to just stick to the A and B that we already have. So condition 1 says that Heloise bought a total of 10 stamps. Well, we articulated the types of stamps as A and B, and we know that A plus B from this information is equal to 10. And of course, there are a litany of possible values for A and B. It could be 1 and 9, 9 and 1. Just thinking about this in the abstract, we can really quickly say, well, that is just a single equation, bunch of different possibilities, so we eliminate condition 1 alone from being sufficient, and we know our options remain as B, C, or E. Then, condition 2 says that Heloise spent a total of $4 on stamps. So now we've got to incorporate the cost of each stamp type. So we know that 25A, so 25 cents per A, plus the 20 cents per B is going to be equal to the total. Now, make sure you don't confuse the dollar with the cents, so let's just convert that dollars into cents as 400. So now, with word problem data sufficiencies, when the algebra is this direct, you probably want to make sure that there's not like just one outcome that's possible. So we can simplify this for ourselves really nicely. Just divide out 5 from all of the coefficients. So we simplify it as 5a plus 4b is equal to 80. And just looking at this, we can see that there are multiple possible values. We just need to make sure that our b is going to produce a multiple of 5 when multiplied by 4. So b could equal 5, b could equal 10. So as soon as I see that b could equal 5, and then there'd be one set value for a, or b could equal 10, and we'd still be able to get a multiple of 5 out of our a's, we know we're looking at more than one possible outcome. So this condition 2 by itself also not sufficient, and we can eliminate choice B from consideration. But when we consider the two conditions together, we already have two equations with no new variables. So that means without actually doing the math in either a system or by substitution, we know that these two conditions combined are sufficient, and we can select C without doing excess work. So that's how you can work through a word problem data sufficiency. Let's go ahead and take a look at another word problem data sufficiency, this time a yes-no. So we have another scenario, and once again, we'll start with what we know. And so to start, we've got during a 5-day rodeo, so we'll just say days is equal to 5. We find out that the least number of tickets sold for a single day was 800. So least ticks, meaning tickets, of a day is equal to 800. And our question is asking, was the average tickets per day greater than 1,000? So once again, we've got our question, we'll box it off, but we want to consider what we need algebraically before getting to those conditions. So we start, and we know that we've got 5 days of a rodeo, and we know how to solve for an average. So we know that the sum of the tickets, we can just say that's S. And if the sum of the tickets is S, we know that S divided by 5 now has to be greater than 1,000, because that's how we'd actually get our average. So we can multiply this inequality by 5 and determine that what we really need is whether or not S is greater than 5,000. Because if the sum of the tickets is greater than 5,000, we know that the average ticket per day is greater than 1,000. So, and we also already know what our least tickets of the day is, and we can use that to help work through this information. So then, condition 1 says that for the 3 days with the greatest number of tickets sold, okay, the average of the tickets sold per day was 1,200. So the average of the top 3 days is equal to 1,200. So that means that the sum for those 3 days is equal to 3,600. And now, since we know that the least number of tickets per day is 800, well, that means that our minimum of the tickets sold is going to be equal to 3,600 plus 800 plus 800. So 3,600, oops, pretty bad 6 there, plus 1,600, which is going to be equal to 5,200. And of course, that's greater than 5,000. So sure enough, algebraically, we already know that we're looking at a circumstance where condition 1 is sufficient, because we determined that the sum is going to be greater than 5,000, meaning that our answer choices remaining are either A or D. Then condition 2 says that for the 3 days with the least number of tickets sold, the average of tickets sold per day was 900. So the average of the least 3 is equal to 900, which means that the sum for the least 3 is equal to 2,700. But now we've got a different minimum, because our minimum here is going to be equal to 2,700 plus, again, that 800 plus 800. So 2,700 plus 1,600, which is only equal to 4,300. But that only gives us our minimum, not our maximum. So we could have 4,300, or we could have our greatest days be really high, and we don't know. So because we don't determine whether S is greater than 5,000, we just know that S is now greater than 4,300, that's not sufficient. So condition 2 by itself won't work to determine whether the average tickets per day is greater than 1,000. So our answer is choice A. And that is how you can work through a pair of word problem data sufficiencies, and you'll want to go ahead and practice with more word problem data sufficiencies on your own to improve this algebraic translation skill that you'll need to excel on the GMAT.